everyone. Let us start lecture 24. We will continue our discussion on passivation. If we see a polarization plot for an active passive metal, so that time the plot looks like this. So, the plot is this kind of plot one can experience. Now, here this segment, of course, this is the cathodic part, and this segment and if we see the E core, this is E core, and if we draw that line this way, we are getting anodic polarization, and this part is cathodic polarization. Now, when we go to anodic polarization, so there are some critical points in this particular active passive plot. So, this is a typical plot for active passive metal. Now, here if we see this is of course E core, then in this direction we are getting higher and higher corrosion rate or the metal dissolution rate as we are going towards anodic polarization side, since this part is M minus Ne equal to M Ne plus. So, ions are forming. Now, it reaches to a maximum, which is maximum I value. This is in the log I plot, which is small I, current density, I can say ampere per centimeter square. So, this particular position, which is the maximum position, we can say that this is I critical. So, it is simply mentioned as I crit. Okay. So, this is I critical position, and corresponding potential we call it E PP, and its PP means primary passivation. This PP subscript PP is nothing but the primary passivation, and this is called EPP is nothing but primary passivation potential. And once this is reached, this is basically the maximum IA that can be possible, or this is maximum dissolution rate when we go from E core towards positive side. Now, once we reach this, if we further increase the potential, this potential is increasing, we would see that the graph is taking a left turn. So, that means graph is moving this way, and it reaches some point which is corresponding to this. This point is also a critical, another important point, which we call it as ECP. So, the ECP means complete passive potential. or complete passivation potential. And corresponding I value, we call it IP, or we can call it as IP or I passive. So, there are several names. So, we will just put it as IP. So, IP is nothing but passive current density, and of course, I critical is critical current density. Fine. And then as the potential is increasing, we will see that the potential is maintained constant. Potential is this current value, which is IP, is maintained in this particular segment. So, this segment we call it passive region. Passive region. So, from, and let us say this potential we put some name E prime. So, E Cp to E prime, we can say this is passive region, where current density remains constant, almost constant. Now, beyond E prime, if we increase the potential further, I could see that the plot is moving rightwards again. So, this particular zone beyond E prime, that can be due to several factors. It can be due to a dissolution of the metal, it can be due to oxygen evolution reaction, it can be due to pitting related phenomena, it can be due to complex ion formation of the metal oxide that has formed on the metal surface, and then further dissolution. So, if it is dissolution related phenomena above EP, if it is related to dissolution, then this particular potential can be termed as E trans, or it is named as transpassive potential, or it can be EP pit, it can be pitting potential. So, there are several names, or it can be either it can be pitting potential or EB, which is nothing but breakdown potential. So, breakdown of the passive layer. So, this particular term, this particular part, or this beyond E prime, beyond E prime, the metal surface, the oxide layer, the passive layer will not have any influence, but rather it can reach to a potential where oxygen evolution can start. Now, interestingly, the oxygen evolution can start. So, and if we check those reactions that is possible beyond E prime, it can be either OH minus equal to O2 plus H2O plus 4E, or it can be H2O equal to O2 plus 4H plus 4E. So, I could see this oxygen gas evolution starts. So, from here we could see that oxygen gas can evolve at a higher potential. But remember, that time it may not be the transpassive potential, because that time the metal oxide layer, the passive layer, may not dissolve. So, oxide layer remains, but the surface acts as a substrate for the oxygen evolution reactions. Now, these critical values we will talk gradually one by one, but first address this part. Okay. Why we come across this oxygen evolution at a higher potential. Now, in order to find that, we have to now get back to Pourbaix diagram. So, if we draw a Pourbaix diagram of iron on the and we are consideration of iron in H2O, if we consider, and then we are talking about polarization of iron in H2O with a different pH. So, if we draw the Pourbaix diagram, this is pH, this is potential, voltage. Now, these are the boundaries. And this is iron region, this is HFeO2 minus, this is OFeOH whole 2, and these are the positions of different phases. We have already talked detail on this particular Pourbaix diagram in phase 1. So, there are two more lines, one is hydrogen evolution line, this is hydrogen evolution line, and there is one more line which corresponds to the oxygen evolution line. So, which is parallel to the hydrogen evolution line. So, it starts arbitrarily, I am choosing some values. So, of course, it is not arbitrary, this value is 1.227 volt. So, if we when pH equal to 0, so and this voltage is 0 volt. So, if we draw that parallel line, so this is another line. So, this is oxygen line, this line is hydrogen line, and if we take a pH of 7, so this is pH 7, right side of it will have water reduction, and left side we have hydrogen ion reduction, and here also if we consider 7, right side will have this particular reaction, and left side of this pH will have again water reduction, but is I have oxygen reduction, but it is in acidic medium. Fine. Now, if we consider some pH, let us say if we arbitrarily take any pH, let us say this is the pH I consider, this is the pH I consider. So, accordingly I need to find out what will be the behavior of polarization plot Let us assume that we are taking a condition where iron concentration of iron ion is iron Fe plus 2 ion or Fe plus 3 ion is Fe plus 2 equal to 10 to the power minus 6 molar, and this potential if you calculate you will see that this is becoming like this minus volt. How come we can get to this value? I can find out E Fe plus plus Fe equal to E naught Fe plus plus Fe plus 0.0592, N is 2 here, log of Fe plus plus ion concentration. So, this is minus 0.44 and this becomes 0.059 into 3 because this is 10 to the minus 6. So, there is a 2 here. So, then it becomes minus 0.617 volt. So, if we try to increase the potential from let us say this particular position, from here I take the potential to positive side, and the anodic as well as cathodic line will have its own existence. So, if we see that plot, well, of course, log I and potential voltage. Now, if we start from this until unless it reaches to this, I will not have I will have very low iron ion concentration, lower than 10 to the minus 6, because as we go down from this point iron ion concentration reduces. So, that means as we go up the dissolution rate will increase little bit. So, that means deposition rate would reduce also. So, that since the deposition rate reduces, the plot would look like this. If we try to see only the plot related to iron metal deposition and metal dissolution, the plot would be fine. So, now here this is cathodic side, and this is the point where I will start having intersection of this point where I can have. So, actually we have this reaction. So, this is cathodic IC, this is IA. So, this point corresponds to the point here. So, this is the potential corresponding to this point. Why? Because at this point iron is going from inert to corrosive zone, because we have already seen that this is the zone where corrosion happens because it forms ions. This is the zone which is inert zone. Fine. So, this is the potential. Let us say this potential is E1, and E1 is nothing but 0.617 as per this. Why? Because from at this particular point we are having transition from inert to corrosion. So, that is what beyond this point dissolution rate increases. Now, when we go up, it is intersecting the hydrogen evolution line at this point. So, this point would appear due to the intersection of metal dissolution and hydrogen evolution line. So, if we try to draw the, and hydrogen evolution has its own polarization line in this plot. So, if we try to see, so that means here pH, we have maintained the pH to be, let us say it is minus, it is 4, let us say. So, pH is 4. So, E equilibrium hydrogen would be minus 0.059 into 4, this much would be the voltage, considering the fact that the hydrogen gas partial pressure is maintained as 1 atmosphere. So, somewhere it will cut. Okay. So, this cut point corresponds to this point. So, that means when metal is dissolving and this is at a lower potential, this is the point where hydrogen evolution happens. So, that means the cathodic polarization for the hydrogen evolution reaction will cut it. So, it will have its own hydrogen evolution polarization line. So, let us say this is my hydrogen evolution polarization line. So, this is H plus 2E equal to H2, and this potential is nothing but volt, and this potential is appearing at pH 4 when the polarization line of hydrogen evolution, and below 7 this reaction happens. So, we are talking about these reactions. So, this becomes intersection point of cathodic as well as anodic portions of two separate reactions. One reaction is metal dissolution and another reaction is this one. So, now as per our mixed potential theory, this becomes our E core, and polarization line, if I want to draw up to this, let us say up to this potential, if I draw, polarization line will be like this. Now, as we go beyond this, so this becomes my steady state potential, fine. So, beyond this, if we go ahead and we go ahead, when we go ahead we could see that we are only considering I A, because current density corresponding to I C is very low compared to I A. This is basically nothing but I A. Okay. So, now it is reaching to I critical. Now, I critical is the point where maximum dissolution takes place, and beyond I critical, that means if we increase the potential further, my I A is reducing to a great extent. Now, this reduction in I A happens when we have already mentioned, we have already seen that this reduction in I A happens when there is a conversion from active to passive state, and this passive state happens when we have oxide layer or hydroxide layer formation on the metal surface, and this particular maximum point corresponds to EPP, that means primary passivation polarized potential, and that corresponds to this point where the polarization cuts the line between Fe plus 2 and FeOH whole 3, and FeOH whole 3 forms on the metal surface and makes it passive. So, that is what, once it covers up the metal surface, then the surface, the electrolyte is seeing FeOH whole 3 rather than Fe, and FeOH whole 3 is a very is an hydroxide with a very low solubility product. So, that means the solubility product is very low, means the iron Fe plus 3 concentration in the solution would be extremely low. So, the dissolution would be decided by the solubility product of that FeOH whole 3. So, the corrosion rate or the dissolution rate or the IA should reduce, and that is what the reduction happens rapidly, and then it appears IP, because that this IP corresponds to the dissolution rate as decided by the solubility product of FeOH whole 3, or other way around, the ion movement from the metal surface to the electrolyte surface. And now, as we increase the potential further, so we are increasing the potential further in case of, if we consider Pourbaix diagram. So, then it is still in the FeOH whole 3 region, that means the passive layer is still there, but we could see that there is a cut point, and that cut point is cutting the line, the point corresponding to oxygen evolution or oxygen reduction line. So, below this we have already seen, below this particular potential and above this particular potential. So, below this potential we have water to be stable phase, and beyond this potential oxygen should evolve. So, that means beyond this potential reaction, beyond this particular line, this particular line, beyond this line reaction will move this way, and below this line, this is beyond this line, and below this line reaction would move this way. So, that is what this particular, between these two lines we have H2O stable zone. So, once it cuts at this particular point, and if we go beyond that, we have to consider this reaction, because this is in acidic media. So, we will start happening, we will start getting H2O equal to O2 plus 4H plus 4E. So, this reaction happens. So, that means this is anodic process, and this anodic process would have its own polarization as decided by the Tafel slope for that particular reaction. So, we will come across this is the polarization oxygen and this reaction. So, we are talking about this reaction. So, beyond this point, though it is still in the passive zone, and we have already know that this particular phase lead to passivity in the metal. So, beyond that passive zone, the passive zone does not change, but we will see that the polarization plot takes a right turn, and here oxygen starts evolving. So, that is what in the previous plot, we could see that oxygen evolution can start depending on the situation what we have just now seen, the interaction between polarization and Pourbaix diagram. So, we will stop now, we will continue our discussion in our next lecture. Thank you.